Hello everyone, thanks for your interest in my work. This project is on mutually shared autonomy for human-in-loop mobile robot navigation, and I'm Bozorgi. The framework consists of autonomous safety in the loop of human control and human skills in the loop of robot autonomy, which combines the operator's experience and capabilities in perception and decision-making in various environments with robot's strength in computational power and sensing accuracy. In the first mode, incorporation of operators' control commands with commands from autonomous safety block learned from demonstration allows a user to freely navigate the robot while guaranteeing the safety of operation. This fusion is based on safety parameters and the minimum distance between the robot and obstacles. Our framework allows online customization of safety arbitration parameters, enabling the user to temporarily modify the level and smoothness of the transition to safety based on humans' observation and experience, which improves the practicality of the navigation system and satisfaction of human in various environments. The second mode, built up on the autonomous safety block from the first mode, enables the operator to transfer his or her skills in structured behaviors to a robot through learning from demonstration, while the level of incorporation between safety and behavioral commands are injected by user-defined parameters based on humans' perception of the task and environment. The operator can apply each of these modes at any time based on the requirements. In order to investigate various aspects of the framework, 4 experiments were conducted. The first 2 experiments would analyze obstacle avoidance capabilities of the first structural block in various conditions and the effect of online user customizable safety parameters. For investigation of human skills in the loop of robot autonomy, 2 behaviors of wall following and human following are taught to the robot, and the performance of this structural block is presented in each case. The first experiment is implemented to test the autonomous obstacle avoidance capabilities in the loop of human control for 3 scenarios and 2 different sized obstacles. The obstacle avoidance commands are generated by a trained shallow neural network based on the pre-processed ranging information from robot's laser rangefinder. As safety is a vital feature, it is learned from an expert's demonstrations. Here is one frame of an experiment you are about to see. The bottom right window is a video clip of the experiment recorded by the top view camera. In the first experiment, the operator navigates the robot toward colliding with the obstacle. The arbitration function should gradually take control from the user and allocate it to the safety block. The bottom left window shows the robot's URDF and its pre-processed ranging information. The operator's command is shown by a blue arrow, obstacle avoidance is shown in red, and the final shared control command is depicted by a green arrow. Similarly, the 2 boxes on the top left represent the linear and angular velocity commands of human, safety, and the shared autonomy in blue, red, and green. The control sharing between the human and autonomy is based on the arbitration parameter, and that also depends on robot's critical state Z and user customizable safety parameters PSH. Z is defined based on the robot's pre-processed ranging information, and PSH defines the level and smoothness of the transition. As you can see, by decreasing the robot's critical state and based on safety parameters, the arbitration parameter smoothly decreases, allocating control from user to autonomous safety. Another item worth mentioning is that as soon as the obstacle is not in the danger zone defined by safety parameters, the arbitration parameter increases, restoring the operator's control over the robot. In this experiment, we would test the online user customizable transition parameters. In real-life applications, an operator may face different scenarios and environments that a predefined level of safety would not be suitable for, and as a result, limiting his or her ability to finish a task. Online user customizable parameters allow the user to cautiously alter the danger zone to suit the specific scenario. Here, the operator should decrease the danger zone to pass through a narrow passage. After the pass, he restores the transition parameters and navigates toward the remaining obstacle, but autonomy steers away from the collision. Now, we want to test the capabilities of human skills in the loop of autonomous control. This mode allows the operator to teach a structured behavior to a robot through learning from demonstration. The output of the trained model is then fused with aforementioned obstacle avoidance command based on the arbitration parameter, ensuring the safety of the behavior. The arbitration parameter itself depends on robot's critical state Z and offline user-defined safety parameters for the behavior. In this work, wall following and human following were selected as examples of required structured behaviors and learned from the operator. Wall following is learned from operator's demonstration in some simple short scenarios. A shallow neural network regressor is used for the training process. Now the trained autonomy is faced with two complex wall following scenarios. Here is the first scenario. As you can see, the fusion between wall following and obstacle avoidance is governed by the arbitration parameter. Offline safety parameters are set by the operator based on his experience of the task and environment, ensuring the safety and smoothness of the operation. As you saw, a model trained from a simple structured neural network was able to mimic operators' behavior and complete two complex wall-following scenarios with human-like performance. A second example of autonomous behaviors learned from demonstration, the operator trained the mobile robot for human following. Human detection and tracking are done using an RGBD camera. Targets, relative position, and distance to robot were chosen as inputs of a 4-layered, simple structured neural network regressor. Output commands of the trained behavior are then fused with obstacle avoidance commands based on arbitration parameter to ensure safety in human-populated environment. For demonstration, a scenario was designed where the robot has to follow the person in the red hat. The second person passes the robot in the front to add distortion and increase the complexity. Third person in blue shirt walks toward the robot to test the obstacle avoidance in a dynamic scenario. We have recorded this experiment from multiple sources, including a top view camera, motion tracking system, robots camera, and RViz. As you can see, when the person in blue approaches the robot, the arbitration parameter drops, giving more weight to obstacle avoidance command. When the situation clears, the robot continues to follow the target. Furthermore, this experiment showed the capabilities of obstacle avoidance in facing dynamic obstacles. Thank you so much for your time and attention.